Okay. Hi, everyone. My name is Alessandro Chiesa. I am a faculty member in computer science at UC Berkeley. I am also a co-founder of Starkware and of Zcash. In this talk, I would like to give you an introduction to recursive SNARKs. I will provide a warning right away that this talk is going to be technical. And the goal of this talk, or at least the motivation of this talk, is that in the last couple of years, there's been increasing interest in recursive SNARKs in the applied and open source community. So I thought that with this talk, it could be a good opportunity to talk about some of the science that underlies recursive SNARKs. So let's get started. First, let's start with the obligatory slide on SNARKs. So like two algorithms, the prover and the verifier. The verifier knows a circuit C and an instance X, an input. And the prover wants to prove to the verifier that they know a witness W that makes the circuit on input X and W, let's say output 1. The key property of a SNARK is that the proof for convincing the verifier is very small. Specifically, it is exponentially smaller than the size of the circuit. That means logarithmic in it. And more precisely, it is polynomial in the security parameter and logarithmic and polylogarithmic in the size of the circuit. Also, many of you know that SNARKs are impossible unless there are suitable public parameters. This is something that is known as the setup of the proof system. And many of you are probably familiar with the fact that SNARKs have different types of setup. I will not really discuss these things in this talk, but just be aware that that is the case. Okay, so this is so we have some common language and notation. That is a SNARK. I would like to now motivate the notion of recursion with respect to SNARKs. So let's use an example. And specifically, suppose that you want to prove the iterated execution of a function f. So that means that you have some integer t, and you want to prove that if you, let's say, apply f iteratively to the input 0, so f of f of f of f, t times, you get some output zt. Okay? So one way to prove that is something that we could call the monolithic option. You invoke the SNARK to prove all t executions at once. Now, this can be done. However, it has some drawbacks. First, this may actually be infeasible. The memory consumption of prover algorithms in many SNARK constructions actually grows linearly with t. So for sufficiently large t, there just won't exist a machine that will be able to do this, even though maybe you're willing to wait long enough. Also, the value t may not be known in advance. Maybe this iterated application of the function is just some ongoing computation, and there's no specific t that you have in mind. So this motivates an alternative, the so-called recursive option. And here the intuition is that what you want to do is you want to prove one execution of f and also the correctness of the prior proof. In picture, it would look something like this. You use the SNARK to argue that one application of f to 0 leads to some intermediate output, say z1. And in the second step, you apply the SNARK again to prove that you can go from z1 to z2 through f. But also, you prove that you verified the prior SNARK. So now this second proof actually attests to the correctness of z2 being f of 0. And you can continue in this fashion as long as you want. And the point here is that through this recursive option, you're able to overcome both of the above drawbacks in that there is no large memory consumption. You're just iteratively applying the SNARK prover on some smaller computation of size f. And you can keep doing this as long as you want without knowing t in advance. So hopefully these pictures point to the difference between monolithic and recursive option. And what I would like to address now is, is this option secure? Is it efficient? To even start asking these questions, we need to discuss what is the goal of recursion? What do we obtain when we recurse things? And one way to do that is through a cryptographic primitive that is known as incrementally verifiable computation. In more detail, an IVC scheme for a predicate omega. And so where does this predicate come from? We're talking about a function f. Well, for example, you can think of the predicate to be the predicate that controls valid transitions. So the predicate says you can transition from output zi-1 to zi, possibly facilitated through some witness, if the function, given the previous output and some witness, outputs zi. Okay, so there's some abstract predicate that models what are valid transitions, for example, transitions according to f. Okay, an IVC scheme is also tuple, like a SNARK, consisting of a prover and a verifier. But now the properties it satisfies are kind of tailored to the setting of recursion. So now let's try to go through them. There are some cryptographic properties. The first one is functionality. Essentially, it says that you can always make progress. It says, if you give me some data that constitutes a valid transition, so you have ZT and ZT minus 1 make the predicate omega happy, possibly through some witness WT, and the IVC predicate says that the prior output and the prior proof are good, then you can produce a new proof for the new output using the IVC prover in a way that will produce an output that the IVC verifier will accept. Okay? Functionality says that if you want to prove true things, you can make progress in this recursion. Efficiency says that you're not allowed to just remember all the prior inputs, all the prior proofs, and just satisfy the functionality definition. It says you have to do something non-trivial. In particular, you want to restrict the cost of each progress, each step, and the size of each proof in each step to be independent of t. So for example, you could make it depend, say, on the size of the predicate, ideally even less than that. But this, for example, rules out trivial approaches. And last but not least, you want this to be secure. And intuitively, this means that if you have some malicious prover that says, hey, here I have some claimed output ZT and a proof by T, and the IVC prover says, yeah, this proof looks good, then it is because the prover knows witnesses, W1, W2, and so on and so forth, that lead to T-valid transitions from the beginning. So you can go from Z1 to Z2 through some witness validly, for example, through the function f, from Z2 to Z3, and so on and so forth. In other words, there is some valid sort of line computation that leads to ZT in T steps. Okay? So these at high level are the proper IVC scheme. And you can see that the syntax and sort of whatever we wrote here is tailored to model this incremental verifiable computation. That's why it's called like that. There's also another cryptographic primitive that we consider in cryptography that is known as proof current data. It is essentially a sort of generalization of incrementally verifiable computation that considers predicates that have multiple inputs. So, multiple inputs. So in this case, the predicate would receive not just one prior output, but multiple prior outputs. And you can think of this visually as, instead of computations that evolve over a line graph, they are computations that evolve over a directed acyclic graph. Okay? The point of this slide was to tell you that in cryptography, we have primitives that capture the desired functionality and security of recursive SNARKs. And these are the primitives. Now, these primitives in their own, they have applications. That's why we study them. One was already known a few years ago was that actually, if you achieve some form of recursion like PCD, you can actually obtain IVC for long chains. And this in itself, in turn, implies SNARKs with extremely good space complexity. To this day, we don't really know many other approaches to obtain SNARKs with good space complexity. You can also obtain SNARKs from MapReduced computations, where proving is itself a MapReduced computation. And perhaps closer to blockchains, you can use IVC to construct verifiable delay functions, and also for succinct blockchains, which have applications to ultralight clients. So in this talk, I will not spend further time on applications. Here are some references that we can use to kind of look up these and these applications. There are actually more. But suffices to say that IVC and PCD are very powerful primitives, and that's why people are excited about them. But these are powerful primitives, and one thing is to define them, a different thing is to construct them. So how can you achieve IVC and PCD from SNARKs? So this leads me to the main part of the talk, which is I want to summarize the foundations of what we know about how to construct IVC and PCD. And specifically, I want to start by zooming into the core of the construction of IVC, which is where you use the SNARK prover to prove that the SNARK verifier has accepted, and also that the predicate has been satisfied. In other words, we want to kind of transform a SNARK scheme into an IVC scheme, okay? The core of the construction is to define a computation that we're going to call it R. R stands for recursive. That is going to check that a new output satisfies the IVC predicate omega. Again, omega is, you can think about it as the transition function f. And that the prior output and proof satisfy the SNARK verifier. In pseudocode, it would look something like this. You have an instance ZT and some auxiliary witness AUX-T. And this computation will check that there is a valid transition from ZT-1 to ZT. And moreover, if you're not in the base case, that the prior output is accompanied by valid proof. And notice here that this computation is recursive because in line 3 here, we have the code of the computation appearing inside the computation itself. Why? Because we'll be making proofs about R. We want to verify things about R at the same time. Now, this looks circular, and I will not linger right now on how you can make this well-defined. But let's say that it is well-defined. If you can make it well-defined, then the IVC prover and IVC verifier follow rather straightforwardly from the construction of R. Specifically, if you want to obtain the IVC prover from the SNARK prover, it would look something like this. The prover would first assemble the computation R from the predicate omega and the verifier V from the SNARK. It will assemble the witness and invoke the SNARK prover to produce a proof for the next step. And the IVC verifier will similarly construct the computation R from omega and V, and it will use the SNARK verifier to verify the sort of new proof relative to the new output. So syntactically, this is roughly how constructing IVC looks like from a SNARK. Okay, but this is just putting together some pseudocode. Is it secure? So this brings us to a theorem from now 7 years ago that says that if the SNARK is a so-called adaptive argument of knowledge, i.e. a SNARK, that's what the K in a SNARK stands for argument of knowledge, then the IVC scheme is secure according to the definition I sketched in the prior slide. Moreover, if the SNARK has so-called succinct verification, this means that checking a proof for a circuit requires much less time than evaluating the circuit itself. Then the IVC scheme is efficient in the sense that we defined earlier. And here the intuition for why you need succinct verification in the construction that we saw in the prior slide is that if that is the case, then recursive circuit R doesn't grow with each step, which you don't want, right? You want to be able to have a sustainable be able to recurse an unbounded number of times. So this holds more generally for PCD schemes, which I didn't discuss. And in some, we know it has been proven that if you have a SNARK with succinct verification, then through recursion, you obtain IVC and PCD. This construction has actually useful additional features. For example, it preserves zero knowledge, in that if the SNARK is zero knowledge, so is the IVC or PCD scheme. Also, it maintains the type of setup. So if your SNARK has either updatable or transparent setup, then this type of setup will just basically be unchanged after recursion. Okay, now the hypothesis for security that the SNARK is an argument of knowledge is a strong requirement. However, fortunately, most SNARK constructions that we have basically already satisfy it. You need to kind of work hard to prove that it does. Maybe you have to tweak the construction a little bit, But basically, almost any natural construction that we have can be proved to be an argument of knowledge. Less convenient is the second restriction, the one that we need to require that this SNARK has succinct verification. There are SNARKs with nice properties that have small proofs but do not have succinct verification. So it would be nice to somehow relax this requirement. So this leads to the next slide, which is last year, in a very nice paper, it was observed that for recursion, you don't really need to require the SNARK verification to be succinct. Intuitively, for recursion, it should be enough to incrementally update a state that remembers the conjunction of a validity of past proofs. You don't want to literally check them. You just want to remember the end of whether they're all satisfied, okay? And then you can verify this conjunction outside the recursive circuit. In a more recent paper, this has led to the notion of SNARKs with accumulation, which allows us to expand the reach of recursion to new constructions of SNARKs. Now, because this is a technical talk, I will actually attempt to explain what is an accumulation for a SNARK. So let's try to do that. We say that a triple PVD, that is a prover, verifier, decider, is an accumulation scheme for a SNARK if several properties hold. The first one is functionality. Intuitively, it is we want to make progress. So we're going to fix a circuit, an instance X, and a SNARK proof pi, and then something known as an accumulator. In this case, this is the old accumulator. The goal of the accumulator will be to remember the conjunction of the validity of all prior proofs. And if the accumulation decider determines that the conjunction is 1, and also the kind of new SNARK is valid, then it is possible to produce a new accumulator that kind of folds the new SNARK into the accumulator in such a way that the new accumulator looks like it was indeed produced from the previous SNARK and old accumulator. And the accumulation decider agrees that the new conjunction evaluates to 1. Okay? So in other words, you have some accumulator, you can keep throwing into it new SNARK verifications in a way that at the end, you can check whether if there ever was a SNARK that didn't verify, then the conjunction will evaluate to 0. But if all of them were good, then it will evaluate to 1. Efficiency here says that, again, you're not allowed to cheat. Like the sizes of things just depend, say, possibly on the circuit, but they're independent in a number of accumulations. And security says that if a malicious prover is able to somehow produce a new accumulator that is valid, and this new accumulator is properly produced from an old accumulator, then you can infer that because the new accumulator is valid, the old SNARK, the SNARK that was folded into the new accumulator is also valid, and the old accumulator is itself valid. So it lets you kind of travel into the past. That's why for security. So it is a bit of a mouthful, but intuitively, the intuition is that we're not verifying SNARKs. We're going to remember the end of all the SNARKs we've encountered so far. Armed with this tool, we can now modify our paradigm. Rather than proving that the SNARK verifier has accepted, we're going to prove that the accumulation verifier has accumulated. So our new goal is we're going to obtain IVC from a SNARK with accumulation, which is a more relaxed requirement than SNARK with succinct verification. Again, the core of construction is to define a recursive computation, let's call it R again, that checks that a new output satisfies the IVC predicate, like before, but now it will check that the prior output and proof were correctly accumulated. And here is the pseudocode for that. You see here we have added an accumulator in the instance for the circuit, which will remember the validity of all proofs, say for I less than t. And in here, the only difference is that instead of checking the SNARK verifier, we're going to check that a new accumulator is correctly derived from the old one. And given this recursive computation, the IVC prover and IVC verifier follow immediately. The IVC prover will assemble the recursive computation from omega and the accumulation verifier. it will compute the new accumulator from the old one, and then it will pass these inputs to the SNARK prover who will produce the proof to pass along. Notice that we're passing along not just the proof, but also not just the new proof, but also a new accumulator. Why? Because in the IBC verifier, we're going to check that the new accumulator is valid and that the SNARK proof is valid. So this is syntactically what happens, how you use accumulation. And in the same paper that introduced accumulation schemes, it was proved that if the SNARK, again, is an adaptive argument of knowledge, and the accumulation scheme is sound and secure in the way that we saw in the prior slide, then the IBC scheme is indeed secure. For an efficiency standpoint, we only need the SNARK to have accumulation. And crucially, we do not need the SNARK verifier or the accumulation decider to be succinct. The only thing we need is that the accumulation verifier, which indeed appears in the recursive computation, is succinct. So this holds more generally also for PCD, and we learned that SNARK with accumulation does lead to IBC and PCD. This type of recursion also preserves nice properties like zero knowledge and setup, like the prior one. Good. So we've discussed two types of recursion. I want to dedicate just one slide about post-quantum security because, for the long-term security of blockchains, eventually we're going to need not just post-quantum SNARKs, but also post-quantum recursive SNARKs, which means post-quantum IBC and PCD. Hopefully, it is clear that if the SNARK itself is not post-quantum secure, then we have little hope of, it's not going to be the case that anything we build from it is going to be post-quantum secure. So let's ask the question of, what if we start from a SNARK that is post-quantum secure? For example, essentially any of the hash-based SNARKs out there are plausibly post-quantum secure. The main challenge to show that after recursion you obtain a scheme that is post-quantum is the fact that a malicious prover may be probabilistic. This doesn't sound so scary, but let me explain why probabilistic adversaries, probabilistic provers are problematic for recursion. Let's say you start with a malicious prover that outputs some claimed output ZT and proof pi t. In the proof of security for recursion, we're going to apply the argument of knowledge property to obtain an extractor that produces a witness for the recursive computation statement. In particular, we'll obtain a prior output and a prior proof. From this extractor, we are able to produce a prior adversary that produces the prior output and prior proof, and it will have its own extractor and so on and so forth. In this way, we're able to prove security because we obtain the chain that led to ZT. But now we have a problem. How do we know that the prior output produced by the extractor ET and the malicious prover PT-1 are the same? We need them to be the same. Otherwise, we get this disconnected chain leading up to ZT. We need that connected chain. In the classical case, this is easily fixed. We just fix the same randomness, the same random string for the extractor ET and the prover PT-1. But for quantum security, there is no way to couple the random choices of ET and PT-1. That is because quantum circuits can generate their own randomness by basically, for example, measuring a qubit in superposition. So there's nothing to fix across the two. So this was studied recently, and the solution that was used to study this was to rely on a suitably defined post-quantum adaptive knowledge soundness that can be achieved in certain conditions. And this was shown to suffice for recursion from succinct verification, the first type of recursion we saw, and recursion from accumulation, the second type of recursion that we saw, so that we have post-quantum foundations for recursion in both cases. Okay, so in summary, for the foundation part of this talk, there's a lot of SNARKs out there. Here's, for example, some names. We know from theory that SNARKs with succinct verification recurs. In fact, not just that, but in fact, all SNARKs with accumulation also recurs. And this, for example, includes constructions like Halo, which do not have succinct verification, but do have accumulation, which is great because it lets us recurse them. Okay, so that's all I really wanted to say about foundations of recursion. Because many of you are sort of developers and practitioners, I want to talk a little bit about practice, because we want to try to leverage this understanding of recursion and turn this into something that can be used in practice. And the first thing, when you are somebody working recursion, the first thing you are faced with is the recursion is very expensive. First of all, even in standalone use, snark proving is expensive on its own, never mind recursively. It's just a heavyweight cryptographic primitive. But in recursive use, proving is only more expensive. And not just in a vague sense, there are very concrete reasons for why proving recursively things is more expensive in IVC and PCD. So let me explain why. So here is the pseudocode for the two types of recursion that we saw in the foundations part of this talk. One problem is that you're going to have to prove the IVC predicate omega as part of this recursive computation. However, and I didn't really explain this, but the way straightforward approaches to resolve the circularity, right? So we have R here and R here, right? So we have this apparent circularity. Straightforward approaches to break the circularity actually incur schemes in which you will have to universally simulate the IVC predicate omega, which is very expensive. What does universal simulation mean? It means that for every logical gate of omega, you're going to have some set of gates to figure out what is the gate, what is it connected to, and just parse it. And it's going to have like a multiplicative blow up in cost that is rather impractical. Another thing that happens is that you're going to have to prove the SNARK verifier or the accumulation verifier within the recursive computation. And for reasons I'll mention shortly, straightforward approaches to express this type of computation in the SNARK's own language are prohibitively expensive. So there are two concrete reasons, each of which on their own make recursion expensive. And any practical solution for recursion is going to have some way to address these. So let me tell you at high level what in the last few years we have developed as ways to cope with these. First, how do we cope with the cost of proving the IVC predicate omega? One approach to do that is through the feature of preprocessing. Some of you may have heard of the notion of preprocessing SNARKs. Essentially, that means that you have a procedure that's called preprocess that in an offline phase is able to take the desired computation, in this case, recursive circuit R, and produce from it some proving key for R and a short verification key for R that will be used by the SNARK verifier to check proofs about R. What this lets us do is that now we're actually able to define a recursive circuit by passing in this short verification key, for now it's generic, and including it where we will eventually want the verification key for R to be. So it's like some additional input to the circuit. And because it's short, the circuit can actually receive it as input. And later, we will set this verification key to be the short verification key for R, so that actually it will be possible to pass to R a short cryptographic summary of itself to use inside it. Now, I will not get into the technical details, but one can prove that for any preprocessing SNARK, the cost of proving a recursive step, for the reasons that I just described, is essentially the same as the cost of proving omega standalone. So one way to conceptualize that is as follows. Let's say that I want to compare the cost of IVC prover to prove a recursive step of omega versus the cost of the SNARK prover to standalone prove omega, right? So obviously, I'm constructing recursive SNARKs. I shouldn't expect to be faster than just standalone proving omega. So let's just compare our recursive cost against the baseline of just proving omega standalone. Okay, and let's see what happens as omega tends to infinity. Now, by construction of the IVC prover, this is essentially the cost of the SNARK prover on the recursive computation R depending on omega. And for preprocessing SNARKs, one can prove that this limit is 1. Namely, as omega grows large, the each extra new gate will cost you no more than standalone proving that extra gate of omega. So that's great. Like, this is essentially telling us that there is no universal simulation. There is no multiplicative cost on the size of omega. That's great. And indeed, in practice, this makes a huge difference. But there's a reason for that. There's like some fundamental important properties of preprocessing at play. So this is the major technique to cope with the cost of proving omega. What about how do we cope with the cost of proving the SNARK verifier or accumulation verifier? Here, the main problem is that, as I mentioned earlier, expressing the verification in the SNARK's own language leads to overheads. So if omega is not too large and you're not careful, the relative size of the SNARK verifier, accumulation verifier, is going to be huge. And the specific reason for why this is the case, first, it's actually why it happens is pretty curious. And the specific reason for why this is the case depends on the type of preprocessing SNARK. So here's a little table. In SNARKs built from discrete logarithms like bulletproofs, or pairing-based SNARKs like GOT16 or Marlin or Plonk, we have some elliptic curve underneath. And there is this problem that the size of an elliptic curve group cannot equal the size of the elliptic curve base field. This comes from number theory. And this causes some, basically, it means that the computation of the verification is defined over a field that is different from the field of the SNARK's language. This causes a so-called characteristic simulation, which, if you are not careful, it's extremely expensive and causes huge overheads. So one of the major approaches to cope with this is to use so-called cycles of elliptic curves. So it's like two elliptic curves that are made to match their own parameters. For hash-based SNARKs, the main problem is that there are many hashes in the verification computation, and each is expensive when represented as a circuit. And the main approach to address this is to use algebraic hashes. These are hash functions that have smaller circuits by virtue of using the fact that they're defined over large fields. So at high level, this is how we're going to, people have devised ways to cope with the cost of proving the verification. And on top of this, you need a lot of other ideas to turn these into efficient designs. Now, these things together have led to constructions of recursive SNARKs, specifically constructions of IVC and PCD, in practice with some modest numbers. They're acceptable. They could be much better. It would be nice to have them much better, but they're kind of good enough for some applications. So, for example, if you take pairing-based SNARKs, like, for example, GOT16, which has a circuit-specific setup, and Marlin, which has a universal setup, if you don't care about recursion, you're going to use an elliptic curve such as BLS12. And in this case, the size of your verifier as a circuit is going to be huge, like tens of millions of gates. However, if you use instead a cycle of elliptic curves, such as, for example, MNT4, MNT6, you may have heard these, the size of the verifier can be made to be something rather modest and something we can deal with. Let's say 200,000 gates for GOT16 and 600,000 gates for Marlin. Now, using these alternative gates has repercussions that are a little bit unpleasant. For example, the per constraint proving time blows up by a factor of 10, and the argument size goes up by a factor of like 2.5. But in reasonable applications, these are costs we're willing to absorb, and we win much more in reducing the size of our verifier by switching the curve than we lose in these blowups in per constraint proving time and argument size. In the case of hash-based SNARKs, which have transparent setup, if one were to use a hash function that is so traditional, like SHA-256, you're going to obtain a SNARK verifier that is going to have tens to hundreds of millions of gates, something completely impractical. But if you use some of the more recent modern designs of algebraic hash functions like Poseidon, for a proof system like Fractal, which is a preprocessing SNARK, one is able to obtain a verifier that is, say, on the order of 1 million constraints. Again, here, this has repercussions. It makes proving about 10 times slower, and the argument size, fortunately, is not much bigger. But again, we're in the same situation that if you want recursion, you're just going to absorb these kind of trade-offs, and you're happy that you have a verifier. There's not enormous. In the case of a recursion from accumulation, this is a much more recent technique, and there's lots of exciting ongoing engineering work that I'm not going to talk about right now. So this concludes the part of the talk that is about practice. So I would like to summarize what I've discussed in this talk. So recursing SNARKs is useful, but you need to know what that means. And that's why it is important to know that this goal is captured using cryptographic primitives such as incrementally verifiable computation and proof counting data. And we know of several approaches to achieve these, specifically from succinct verification and from accumulation. Preprocessing, curve cycles, and algebraic hashes are important tools to improve efficiency, especially if you want to achieve recursion in practice and build systems with it. This was a technical talk. It was also an experiment for me in that I haven't given this type of material in this audience. Curious to hear feedback and questions about this talk, and I hope you learned something about recursive SNARKs. So yeah, thank you for your attention.